Another interesting application of standard deviations occurs in the world of symmetric and bell-shaped distributions, as you see here. So symmetric and bell-shaped. We will later have a much more detailed chapter that will describe these types of distributions in much more detail. But for now, we have a little early look at how we can use standard deviations with them. These curves tend to describe populations of observations, which means when we're looking at the actual curve itself and describing where things are on the x-axis, then the center of this will be best described by mu, the population mean. If you recall, standard deviation was all about spread. In other words, spreading mu both ways from the center of the distribution. So turns out that if we go about this distance away from the mean, that represents about one standard deviation. So we're going to say that this is, for the purposes of this exercise, is going to be mu plus one standard deviation. Just remember, we are dealing with population values, mu and sigma, not their sample counterparts, x bar and s. So again, if we go the other way, then we're going to go about minus one standard deviation in this direction. We can do the same and keep on going away from these markers. So if this is mu plus one standard deviation, this right here looks like a distance of another standard deviation. So therefore, this is going to be mu plus two standard deviations. This will be over here mu plus three standard deviations. And the same thing on the other side. Mu minus two standard deviations, mu minus three standard deviations. Okay, before we jump into anything else, I do find that sometimes this whole concept with this curve and populations and mu and sigma can be very confusing for students. So I'm just going to pop up an example here to get you, so you can wrap your head around this a little bit better before I introduce anything new. It says the distribution of SAT scores in the US is known to be symmetric and bell-shaped, with a population mean mu equals to 1050 and a standard deviation 210. So what does that mean? So if all the people in the United States took the SATs, all the scores, the mean of those scores would be 1050. So we know just from our distribution right here, our bell-shaped curve, that the middle is always going to be the population mean. So that means this right here is going to be 1050 in our example. Okay, so here's the explanation, essentially. So basically underneath this curve represents all the people who took the SAT scores. All of their scores, basically, are underneath this curve. So the grand majority of people that take the exam fall here at the highest peak, and it's near the middle of the distribution. And you could see that if you start going away from the score, either lower or higher, less and less people are actually earning those scores, which should make a ton of sense, because we're not going to have a lot of people that are going to end up scoring super low or super high. That's just not the way these tests work. Most of the people are going to be scoring somewhere in the middle, and that's where most of the observations fall, hence why there's a higher peak. All the tests are basically jammed into this curve. Okay, so if we follow our standard deviation example, our standard deviation is 210. So it says if you go approximately about this distance, which by the way is associated with where this curve starts to go down and then up again, there's a point somewhere in here where there's a change in what's called inflection, called an inflection point, and that's usually where our first standard deviation marker is. Well, I'll end up talking about that a lot more later when we get into these symmetric and bell-shaped distributions more. But for now, we know that the distance from here to here is going to be 210. So therefore, all we have to do is add 210 to 1050, and that's going to give us 1260 as our first standard deviation marker. Same thing goes the other direction. All we have to do is subtract 210, And that's going to give us our first standard deviation marker below, which is 840. So when we look at this, we could look at this and go, wow, like, so if we were to just mark these by where they are, like, look at all the observations that are in here. That's a lot of observations as opposed to the rest of the curve. So the grand majority, I would assume, of people are going to score somewhere in this range. We will get into more detail in that in a couple minutes. Okay, keeping on moving. So remember, if we go up to here, remember we go 2 standard deviations, 3 standard deviations. So we just want to keep adding 210 to each score. So this is going to end up being 1470 and 1680 on this side. And then on the other side, we're going to keep subtracting 210 to get 630 and 420 as the remaining markers of our SAT scores on this bell-shaped curve. So again, what does this mean? Because the curve is so low over here, there are not a lot of people scoring between, let's say, 420 and 630. There's just not a lot of observations over there, and that's true in real life. Same thing on the other side. There's not a lot of people scoring between 1470 and 1680 on the SATs, whereas there are a bunch of people in here that are scoring more towards the mean score of the SATs. Okay, so let's get to the important rule of the day here, the empirical rule. So the empirical rule is a way to describe the percentage of observations that fall within standard deviation markers. This is very important because what it does is it allows us to get a general idea of how many observations fall underneath the curve. We've already briefly discussed tiny details of that only because in this example, there were a lot in here, a lot of observations, but there weren't so many down here. Well, now we're going to find out exactly what percentage of observations fall in certain regions. Okay, so we're going to start with the first standard deviation markers. If we were to highlight this entire region, and we were to, let's say, compute that area, which we'll talk about a lot later, but generally, if you go 1 standard deviation each way in a symmetric and bell-shaped distribution from the mean, then that will always be exactly 68% of all the observations in that population. So basically, almost 2/3 of the population will fall there. So if we go to our example down here, then between 640 and 1260, we know that 68% of the people that take the SAT scores are going to score between those two values. That's a lot. That's almost 2/3 of the people that take the SATs. A very interesting observation. Okay, moving on. Let's say we went 2 standard deviations each way. 2. So that would be something that looks like this. That would be all of this. So we clearly know that that's going to be larger than 68%. So what we do know for sure, based on the empirical rule, is that that will make up 95% of the entire curve. So therefore, if we were to go to our example down here, if we went from 630 to 1470, a whopping 95% of all people that take the SAT scores are going to score between these two values, which means only 5% will not. That is a pretty significant finding. And finally, if we were to go all the way to 3 standard deviations, each way from the mean, and we were to highlight all of this, all of it, obviously it's going to be bigger than 95, right? All of it. Then we would go, I'm going to put it up here, even though it looks weird. Put it up here. That would make up 99.7% of the entire curve. So again, if we were go to our example, we would say between 420 and 1680 would make up an even more whopping 99.7% of all SAT score takers. Again, this is something that always happens in symmetric and bell-shaped curves, later to be called normal curves, by the way, to be more specific. But this is a trait that happens to occur in all of these types of curves. Okay, so let's speak generically first. Note that the empirical rule, which is the worded way to say this, is often, believe it or not, called the 68, 95, 99.7 rule. I've seen that in many textbooks. So basically, in summary, it's a way to describe the percentage of observations that fall between standard deviation markers in a curve from the mean. But the best thing to do is to go beyond what we just saw here in this example. So we were able to do the very basic and apply 68, 95, and 99.7 to this SAT scores. But what if we chose a little bit different types of questions? Let's check it out. Okay, so I've put some problems over here on the right so we can sort of tackle them and see how we do. It says find the percentage of observations below 840. Okay, so you'll see that 840 is located right here. So 840 is most commonly associated in this example with the 68%, because if we were to mark off this value, then this would represent basically 68% of the curve. But we're looking for below 840. I claim this shouldn't be too challenging, only because there is a ton of symmetry in this, and all we're really dealing with is area. If you took this entire curve right now, it would represent 100%. So all we have to do is figure out how much area is within this region right here, and we should be good to go. So the question is how do we find that? Well, there's several ways to do this. A different student can come up with a different way. What I find is the best way to talk about the whole curve is the fact that there's 100% in the whole curve, which means that there is 50% in half the curve. Okay, so that makes life a little bit easier for us. Why? Because if this is 68% and this whole thing right here is completely symmetric, that means that half of this is going to be 34%. And if there's 34% there, and then this whole thing is 50%, then that makes this right here 50% minus 34%, which is going to give us 16% of the observation. So what does that interpret for us? That means 16% of all people who take the SAT scores are going to fall below 840. Okay, so I reset the curve so we can use it again in order to find our letter B, which is above 1470. So if you look at 1470, that is associated basically with our 95% right here. So if we were to go 2 standard deviations each way and we highlight this entire thing, then this represents 95% of the curve. But we only want above that, which is this all the way this way. Okay? So we're going to do this the same way that we did the other one. We know that if we actually highlighted all of this in here, that's going to represent our 95%. But we can also basically cut that in half, right? We can cut that in half by taking down the middle, right? We want to take half of 95% for our scenario here. So if we take 95 divided by 2, we're going to get 47.5, which means this right here is 47.5. All that's left over on this side of the curve happens to be this little aqua color region that we have here, and we already know that all of this way is 50%, which means in order to find the area that we want, which is right here, we just have to take 50% minus 47.5%, which looks like it's going to give us 2.5%. as the area above. So only 2.5% of the people that take SAT score above 1470 in our curve. Okay, so if you understood letter A and B in my examples here, then letter C should be pretty much along the same lines. If we were to look below 420, you'll see that's going to be at your third standard deviation mark, which correlates to 99.7%. So if we were to basically go through this entire curve from 420 to 1680, then what are we looking at? We're looking at an area of 99.7%. So what does that mean for us? Well, again, if we cut this curve in half and we take half of 99.7, then we're looking at about 49.85. So 49.85 on this side from 420 to the middle spot. So what we're looking for is, believe it or not, we're looking for what's on the other side of this. Now, it's kind of misleading because it doesn't look like the curve is either on that side, but there is a tiny little amount on that side. We already know that this curve on this, the half the curve, no matter what it is, symmetric and bell-shaped, is going to be 50%. That clearly right there is not 50%. There's a little bit left over. So we're going to take the 50%, we're going to subtract the 49.85%. And that is going to give us 0.15%, which means that below 420 is going to give us 0.15%. I do want to reiterate then that there are other ways to do this. And you might have noticed in A, B, and C, there might be a way that fits better in your brain. For example, let's just looking at A again. Below 840, right, represents all of this. Well, we also know that below 840 has to be the same as above 1260 because it's perfectly symmetric on both sides of this distribution. Remember, symmetric, right? So if we know what's here, which we do know, which is 68%, then we should be able to subtract that from 100% and just divide by 2, because that'll give us, subtracting 100 from 68% gives us our value 32%, but that would be for both of these, and since they're symmetric, you can divide by 2 and get 16%. You can do that for any one of these actually in order to get the result. If you like that better, that's perfectly fine. For whatever reason, I find working with just one side of the curve tends to help student brains a little bit, but that's up to you on how you feel and what is comfortable for you. Okay, the last one here is just a little bit trickier. So let's take a peek. We're going between 840 and 1470. So we're basically dealing with this region right here, which I will shade in my yellow highlighter here. Okay, so if we're dealing with this region, you'll notice that it doesn't exactly apply to the percentages in the empirical rule. Even though we do happen to have one value from 68 and one from 95% in terms of their exterior endpoints, that actually will help us. But the key is, for me again, is all you really have to do is you have to figure out what this is, and you have to figure out what this is. And I claim we've kind of already done that, because this region right here is half of our 68%. So if we go half of 68%, right, we're going to get 34%. Whereas this region over here is going to be half of our 95% because of symmetry. So that's going to be half of our 95%. Half of 95 is going to give us 47.5%. So if we know both of those things, then all we have to do is add them together to get the result that we want. So if I just put that down here, we could do 34% plus 47.5%. We put that together, we're going to get 81.5% of the observations. I do find that the empirical rule is an excellent way for students to visualize mean and standard deviation earlier on in the course. We don't actually talk about symmetric and bell-shaped distributions at least for several weeks, maybe a month. So it's very important, at least for now, for you to visualize this and to get an idea of how percentages work underneath the curve.